This is my first video, so please be kind. This video will hopefully be part of a series about my experiences as a maker, covering topics on CNC machining, additive manufacturing, and hopefully the business aspects of C&L Workshop LLC, also known as Candle. This video is specifically about what I would term the acceptance testing of my OneFinity Elite Foreman upgraded with a Sola Fide Designs KC spindle kit. My apologies for pronunciation of that, Nick. I would warn you this is going to be basically a PowerPoint presentation. What can I say? I was an engineer. I did these for over 40 years before I retired. What am I doing and why? The one is basically measuring the system runout at the bit shank. Why am I doing this? Well, runout is the manufacturing error that every round part ever made has. Basically, it is the wobble the piece experiences as it revolves around its axes. If we look at an extreme case, we can now see how runout affects your surface finish. As the bit moves left to right, it leaves behind a washboard or corrugated surface, not the desired result. You should also consider that because the bit is not seeing a consistent depth of cut, it is not seeing a consistent force being applied to it either. Basically, the bit is seeing a pulsing with the cutting force and therefore deflection. Kind of reminds you of bending a paperclip, doesn't it? This leads us to how does runout affect your tool life? Here are a few images from the web. The left one gives us actionable data. There is a bunch of parameters missing in this chart, for example, bit material, cut material, I could go on. But I think the chart is still applicable in a broad brush manner. Looking at the chart on the left, the bottom axis of percent total indicated runout divided by the chip load. Using Harvey Tool's data for hardwood, an 1/8 inch bit, finishing pass chip load is about 0.0036. Assuming our TIR is about 1 thou, our percentage is about 30%, or we should expect to see about 85% tool life. Double that TIR to 2 thou, and our tool life drops to 40%. Now that explains why small bits don't last long at all, doesn't it? So let me talk a little bit about my metrology setup. Metrology is just a fancy word for the science of measurements. I have a Matoyo dial test indicator with an accuracy of about 1/2 thou. I hold the indicator with a Naga gauge holder with a magnetic base. I even raided the garage for a steel weight plate from an old garden tractor to secure the setup. I would consider myself an entry-level journeyman machinist, which means I know to preload the gauge and be wary of cosine error. As I mentioned before, every part that spins has a runout associated with it. Now I can't realistically measure every part that adds to my runout. Think the internal bearings of my spindle. I just can't get to those. But I can measure the runout at major interfaces. This should be able to give me a plan of attack to minimize the total runout, basically identifying the weak links. In this picture, I could measure the runout of the spindle, the tool holder, and the bit. In the worst case scenario, all the runouts add up. In the best case scenario, some of the runouts cancel each other out. This can lead to a game of chase the runout, a game I try to avoid as I'm not very good at it. Considering the quality of the gear I could afford to buy and use, and looking at the stack-ups, anything under 1 thou is in my expected ballpark. My dial indicator has a 1/2 thou graduations, which means I can guess down to maybe 1/4 thou. Reading literature on runout leads me to believe I should have a runout of less than 20% of my chip load. Looking at the difficult but not worst case scenario, again using Harvey data, a 1/4 inch end mill in MDF has a chip load of about 9 thou. So an under 1 thou runout reading is roughly 10%, well below the 20% anticipated chip load. Before I jump into the test, let me do a quick calculation as to what I expect. As you can see, the limit of what I can afford for tolerance is about 2/10 of a thou per component, which should give me a worst case scenario of about 9/10 of a thou. Now this is where things got a bit wonky. I tried to measure the runout on the spindle, and frankly I could not see anything on my gauge that I could not rationalize away. Yep, bump table, dumb stuff like that. was really trying to take the temperature of a raindrop with a turkey thermometer. This is when I reached out to Alex at CNC Depot. He has given me a video that uses a much better gauge. Notice his gauge reads 1/10 of a thou, and you might be able to see 1/10 if you squint real hard. So Spindle seems to be doing what it's supposed to do. I then jumped right into the final test. What does the whole contraption I have for a runout? I'll be generous in saying that I'm seeing maybe 1/4 of a thou. Let's face it, I'm at the limits of what I can measure. Before people start typing away in the comment section, I know that spinning the tool with my hand is a bad practice. My hand will cause a force pulse, which will cause my readings to look worse than they really are. I'm guessing at 1/4 of a thou. Really? I'm okay with that. Returning to my expectation slide and updating it, I'd say I'm pretty happy with what I see, and the results don't seem unreasonable. As the slide says, I think I've reached the point of diminishing returns. I'm pretty confident the machine is good enough for the wife I have. Besides learning about the machine, I've also learned that metrology is expensive, and I'm not very good at it. I hope this video has been of value to you, and while these values are specific to my machine, I believe the concepts are valid from a Makino 5-axis machine to a Vevor 3018. I really try not to judge hardware. We all buy what we can afford and try to get the most out of it. Thank you for putting up with me.